This week we had some housings to make out of steel, and fortunately for me, we actually had 100 of these blanks upstairs from a previous job, and I actually already had a fixture right here to fit them. And this order was only for 80 pieces, so I figured let's use that. So here we have 3 parts. There was originally 3 parts on each side of the tombstone, but because the order wasn't that big, I'm only doing it on one side. But same thing as most of my others, edge grippers on one side, pit bulls opposed to them. Loading up my favorite 2.5-inch dormer high feed mill here. Got it lined up with the tool setter, push go, touch it off real quick to get the height. And now we start the roughing. Now because this is pretty much the same material as the last video and most mild steel machines the same, I started out with the same speed and feed as normal, but as you'll see here, something will start to change in the noise of the cutter after a little bit. Let's see if you can figure out when. So when I heard that noise, I pretty much knew the inserts had probably had it, so I cycle stopped the machine, and as you see here, a couple of the inserts got chipped off. So I just flipped them to a new edge, finished up the last pass, and nothing else happened really consequential with this. Just cut one more pass, and we continued on. So this is me checking the run out on my Sumitomo 14mm MDH drill here. If you look, we got 0 on one flute, and when we flip it around, we got 0 on the other. If there's one thing I've learned in machining, solid carbide drills hate runout, and that is one easy way to break them. So here we are just popping some through holes. This is actually cutting 20 thousandths per revolution, 330 surface footage. It's making some pretty nice sized chips for a drill this diameter. 20 thou per rev is not as high as you could go with this. I actually run it at 27 thou on another job, but it's pretty substantial for this drill. And just a quick look at some of the chips that it makes. Some nice little 6s and 9s. Not a whole lot of heat in these chips, so I probably could up the surface footage, but it cuts pretty well at this rate, so I left it alone. And here's the chip thickness, 20 thou. So next up comes my 3/4 inch 6-flute chip splitter end mill from Helical, just roughing out this center bore. This is ramping down at 3 degrees and something like 5 thousandths per tooth if I remember right. And just showing what it looks like with coolant on when I normally run this in production. So then we take that same end mill and rough out the counterbore, doing one spring pass afterward just to get rid of tool deflection. And then we start roughing the outside. This is taking only a 60 thousandths width of cut, but I believe this is 8 thousandths per tooth at full 1.75 inch depth. So it puts about a 70% load on the spindle. It's taking a pretty hefty cut. And then using that same end mill, we do a quick clean-up finish pass around the outside. Same surface footage, just lowered the chip load down to 3 thou from 8. So then taking the same 3/4 inch end mill from the face, we're going to ramp down helically into this pocket on the side, right on top of one of those 14mm holes. This is going a little slower ramping than it cuts at, I think 75 inches a minute, where it cuts at 183. And the sparks are just because as it breaks through that pocket, the chips get really thin. And it's partially because this tool has probably run its course for useful life. I've done a lot of cutting with this end mill, and it still cuts just like it's new, but the chips do look a little hotter than it was when it was brand new. And a quick little finish pass just to clean up the rough finish on the walls with the reduced feed rate. So this is that 6-flute end mill I've been using to rough and finish everything, and as you look there, there's little notches cut out of the flutes. That basically just makes the chips small, so there's not huge chips in the pockets that I mill. But as you look at the wall finishes, you can't actually see any noticeable lines from where those chip splitters are cut out. So here we're just popping some 7mm holes in next to those pockets. Then up comes my trusty 1/2-inch end mill with a 30 thou corner radius on it. First, it's going to mill out these counterbores. I have it retracting up every time just to clear the chips out so that it's not milling over the chips from the first half of the counterbore. Then next comes the roughing of these top steps on the parts. First we're going to do the lowest one right here. And finishing that lowest step with the same end mill. Then roughing the next highest step up with another 3D adaptive toolpath. I believe this is going an 1/8 inch width of cut and about 160 inches a minute. And then this is the finishing passes on that next higher step. So instead of doing a straight facing pass on this part like I normally would, I actually programmed this as a pocket because I liked the way the surface finish came out and I liked how clean the toolpath was. It didn't have a whole lot of wasted movement like a normal facing pass would. Then we come in and surface the radius on this center counterbore right here with the same end mill. So this is just a spiral pattern surfacing the radius with my surfacing guide I made, and it's doing about a 5 thou step up. The only reason I'm not using a radius cutter for this is because we actually don't have a 160 thousandths radius cutter, so I was kind of forced to surface it with an end mill, which is the same radius you see right here that actually is getting surfaced onto the side pocket from 90 degrees. Then we turn the tombstone to 45 degrees, and I'm going to mill these two 90-degree grooves in the side of the part, actually with an end mill turned at 45, because I didn't really want to do this with a spot drill or another kind of 90-degree cutter where the tip could break off. This is a lot more reliable. I bring up my 228 solid carbide drill and pop the holes in for my 1/4-20s. Followed by the two 5mm clearance holes. So for anyone that does machining and hasn't seen these before, these are helical 5-flute chamfer mills with helical flutes ground into them, and they work way better than any spot drill or mill drill I've ever worked for chamfering with. And here we are just running around the part, basically adding little 10 or 15 thou edge breaks on all the burrs on the part, just so there isn't any sharp edges. And adding some nice little chamfers on the 1/4-20s and those 5mm drain holes. And of course, we don't forget about the 7mm holes on the side either. Those always get chamfers also. Then the 1/4-20 form tap. Because this is only 1018 and the threads are relatively shallow, coolant works fine. There's no need for Molly D or any aftermarket product. And this is the part finished off op 1. Pretty much everything's chamfered. Got the little grip marks there from where the side grippers bit into the material. And because this order wasn't huge, I just decided to stick it in a vise like this. There were two flat sides, so it works out easy. So once it's all done, we come over to the computer and we're going to send the pallet back into the machine, typing in the pallet number here and pushing OK and hitting start. So when I'm doing something like this and the zero isn't that critical, I just bring the probe over roughly in the center of the hole, and then I'm just going to teach the work shift to the machine in P1 there. And that way in the beginning of the program it's able to come over and just go inside. And I set the zero on this part as the bottom. So I touch the probe off the bottom of the vise. I'm going to go to the same work shift, hit teach, input, and it's going to read the zero off the probe's length. So at the beginning of the program here, it just goes right inside that center hole that I drilled all the way through, picks up my XY0 for the work coordinate system. So first cutting tool on Op 2 is going to be this high feed mill that was used on Op 1. And as you'll hear here, high feed mills in general do not like interrupted cuts. And you hear when it goes over the holes, it sounds really bad. So on this cut right here, as it goes over the holes, you can hear something else went wrong with the insert. And just like I had suspected, the insert chipped again. I should have known better than this. I know that high feed mills don't like interrupted cuts over holes, but I tried it anyway, and it didn't work, so we flipped the inserts and go again. I lowered the feed rate 40%, and it seems to have fixed the problem. I tell all our new operators, your ears are the best tool that you have. If something sounds wrong, it usually is wrong. If something doesn't sound like it's cutting smooth, it usually isn't cutting smooth. So use that to your advantage when you get into machining. If you start hearing something chatter, don't just let it go. Try to figure out why and fix it. So back up with the 1/2-inch 5-flute end mill just to rough this hat off the back. I do this because if there's another thing high feed mills do not like, it's unsupported hats of material on the back of Op 2 parts. I always like to rough the hat off with an end mill rather than with a high feed indexable mill. So we're going to come in here and rough out this counterbore in the center. First we're going to do our roughing pass here and then come back in with a slower feed rate for the cleanup pass just to make the finish nice and pretty. Then only because the material is really small, we're going to take the same end mill and just finish the tops of these towers right here and finish the lower step of the part right here. I'm doing this because when I surfaced those towers sticking up, I wanted the blend to be really good, so I wanted to make sure I used the same tool to finish the floor as the towers. Then we start the 3D surfacing of these 4 towers right here. They're actually modeled at like an 8.6 degree angle or something weird like that, so it was easier for me to surface them on there than to try to find a custom cutter for this. So I'm just walking down, going 10 thou at a time. And here on the bottom you can see what that tower ends up looking like when it's done. So we pop one more drain hole in with the 5mm carbide drill, and then comes some grooves for, I'm assuming it's drainage also, for the back of this part. Just a 3D contour ramp down with a 1/4-inch end mill. And last but not least is adding some edge breaks on the rest of the stuff on Op 2. I know I always harp on it on every video, but if you're getting into machining, get in the practice of chamfering as much in the machine as you can. Your deburring department will love you, and it makes better parts having the machine do the chamfers rather than by hand. So here's the part off Op 2. Pretty happy with most of the finishes. This part gets painted so it doesn't have a lot of critical tolerances on the outside, but it came out pretty good. So as far as the CAD goes for this, when I saw this part, I opened the old file for the fixture that I knew that I made a couple years ago, and I basically just came over here, took a measurement to find out what the spacing was between the parts, and then once I knew that, I didn't really have to model the fixture. I knew the clearances would work, so I just patterned the part down 3 times with that spacing, have the 3 parts here along with the 3 pieces of stock. And then if you look here, I just had one part with the stock model for what the stock actually looked like for Op 2. Then after I hide that, you'll see here I have the 4 stock models for my towers. I use this for my surfacing, and if you look here, I extended the surface 10 thou above the model, just so the end mill actually starts above where it has to be. So if there's any height differential variation, it's not going to dig in. Same thing here. Did my trick where I made a 2.5-degree flare out on the top and bottom of all the surfacing pieces, just so that if the end mill height was slightly off, it wouldn't leave a step. So jumping here into the manufacturer workspace, nothing really too complicated with this. As I open this, I have all 3 parts selected for the model, and you see just facing, these are the holes I drilled all the way through and the holes from the side. My bore tool path just to bore out that center counter bore, and in 2D contour just to clean it up. I have a 3D adaptive here that I had to use like this because of the close spacing of the parts. If I did it one and patterned it, it was going to hit the part above it. So I had to do it like this to force it to actually be able to know where the parts were. So this is just a 2D adaptive I used on that side pocket here. Nothing too crazy. Contour to finish, my drilling for the side holes, 2D pocket to rough and finish those counter bores on the face. Then here I actually did a 2D adaptive. I had to draw a sketch for my geometry because I didn't want it to go into those counter bores there. So as you see, I have a sketch with the outside of the part selected as my stock contour so it didn't overcut. And the next step down I actually did as a 3D adaptive instead of 2 because I was okay with the way that it read the stock and the cuts that it was actually making. So I selected the bottom of that chamfer and that face just so it would only cut in between those heights and wouldn't try to cut anything else. So finish it with some 2D contours. Here's the 2D pocket I used for the face. And if you look here when I open this up, I actually selected the outside of the part as my pocket boundary, and then I selected the bore and the outside of the part as my stock. This is my spiral tool path for surfacing that one radius and my 3D contour for surfacing the other one. I actually selected as my model those pieces that I actually made as offset surfaces because if you look there, it actually starts above the face of the part instead of starting right on the top. Just some 2D contours at 45 degrees to finish those grooves. And then the rest of the part is actually just patterned down because it wasn't critical for clearances. So all the chamfering and all the holes are pretty much easy to do like that. So for my linear patterns here, I always select it by operation because that keeps the machine from indexing the B unnecessarily in case you have multiple indexes. So on op 2 here, there's just the stock I selected, my probing for that center hole, roughing it off with the feed mill, my 3D adaptive to rough off the hat. Then we have a 2D adaptive and contour to finish that counter bore, a facing op just to face the top of those towers. And I'm actually facing the inside with another 2D pocket. I did the same trick here. I selected the outside as my stock and the 4 towers as my body there. So for the 3D surfacing of these towers here, you'll see I used a 3D contour path. And as I open this, the edge I selected is actually the surface I made for the surfacing model, which are the 4 bodies that I selected right here, which when I open this tree right here, you'll see are actually the 4 bodies right here. And as I click OK, you'll see that forces the toolpath to actually start above the real model. That way it's not cutting on the first pass, which is what I usually prefer for any surfacing op. So drilling the one hole, then these grooves right here with my 2D contour, and all the edge breaks. Pretty simple from a CAD CAM standpoint. And with that, thank you all for watching, and I'll catch you all next week.